Okay, so today is lecture 9 called Bias and Variance Trade-Off. So this topic is, like I mentioned in the beginning, is extremely important. This is the theoretical foundations of machine learning workflows. Okay, so let's come back. I mean, we actually visited this figure before. We tried to see, I mean, when you have some data given, and there's one really big question you need to ask is, so what type of model I need to fit there? And when you decide the models, or even if you decide this is just one kind of model, what is that hyperparameter? Normally different kind of, like polynomial regression, there are different kind of hyperparameter, you need to tune it. So how do you get it right? So this issue is really about complexity of the model and goodness of the fit. But in the end, what we ultimately looking for or aim for is generalization to future data. So we actually pointed out two wrong cases or two bad cases. So for example, this model, we tried to fit a line there, and we call this type of model underfitting. And so this is underfitting, and the other kind is just the model is just too complex. It makes this really wild decisions when between for those regions you don't have a training points to constrain the model. So this is called overfitting. So in fact, the reason behind underfitting is called high bias, and the reason causes the overfitting is high variance. So this is the topic of today. So we define what do we mean bias and variance, and why do they related to the generalization. So the previous page is a page of this overfitting and underfitting for the regression case, and similar phenomena also in the classification case. So we only covered two kinds of classification. One kind is really the first lecture. We covered a linear classification. You just have a line separated to classes. And the other classifier we just covered is this k-nearest neighbor-based classification. All right, so linear classification, you can actually tell it's a global model, pretty stable, but it make a lot of mistakes actually around this region, right? So this is like the training, even for the training data, I don't predict very well there. And I'm also not predicting very well on the future data. So this is called underfitting. So this is on similar to that linear line regression case, underfitting. And to the other extreme is this one nearest neighbor case. So when you have just one, you only consider one neighbor to make a decision, and you just perfectly fit your training data. There's actually, in fact, zero training error. But so for the testing data, it's actually very difficult to imagine they all fit to this single holes, right? This blue one at all like blue points, and it just it feeds noise in the end. Actually what you're doing is eyeball to make that feeling. It just feeds a lot of noise, which means it fits the training data so well, it potentially just have high testing error. So this is the overfitting case. And the middle, hopefully right. Okay. All right, so I already mentioned when k equals to 1 and k-nearest neighbor, it just gives you 0 training error. So this really kind of alerts us, is minimizing training error into 0 a good thing or a bad thing? So certainly minimizing training error is not always good in this case, right? We don't want this, to be honest. Then what should we truly minimize? All right, so now we start jumping to bias variance trade-off decomposition. So to get this topic started, I have to review something called mean and variance of a random variable. So I hope you still remember the definition of mean is, I think it's the next page, it's just you're taking expectation of the values of that random variable and then proportionally weighted by that likelihood. So before that, I hope you still remember what do we mean a random variable. So we normally write capital letter for random variable, and in our setting, we mostly have random vector. So we can write this is a capital letter with an arrow on top, and there are P random variable included. This is a random vector. And in our setting, we normally also have that output random variable. So we can think about their random variables follow some kind of probabilistic distributions. And then because X is a random vector, this actually makes our fx is also a random variable. The random, okay, so fx itself is also a random variable. We can also think about this theta. So assuming we're trying to learn a linear prediction function, which the function is fx equals to theta transpose x. And this theta parameter can be also considered as a random variable, has some kind of follow some kind of distributions. All right, so random variable. Whenever we talk about random variable, normally what we first can calculate is it's the mean of the random variable or the expectation of the random variable. So I hope you still remember the most basic distribution. What we normally learned in the first probability class is the Bernoulli distribution, which is the heads and tail, right? So you flip a coin, what's the probability of heads up or the tail up? So assuming the heads up is 0.9, then the tail up is 0.1. And then how do you calculate this expectation of this Bernoulli random variable? Very simple. This is exactly what I showed there. It's like ET, the expectation of this random Bernoulli variable is summation of its values, assuming its tail value is -1. So I put -1 there. Its probability 0.1. So -1 times, let me change that to a blue color just to make it, oh, sorry. Yeah. Sorry. Okay, so I hope I can change to a different color. Yeah, I got it. All right, so this is really, so this is equals to summation its value -1 times the probability 0.1, right? So that's the first possible value in this Bernoulli distribution. And then the second possibility is 1, right? T equals to 1. 1 times 0.9. And this is how you get its expected value of this Bernoulli variable is 0.8. So this is the discrete case. You can calculate the expectation. In the continuous case, you take integral over all the possible value of x, still the same equation, x times px. So the most classic continuous random variable is the Gaussian variable. So assuming actually Gaussian variables mean or expectation is the easiest to calculate because that's in fact a part of its important parameters. So for a Gaussian variable, mean 2, sigma as variance, its mean expectation equals to 2. Okay, so this is all very elementary probability. I hope you still remember that. Okay, so expectation can be calculated onto random variable, can also be calculated on top of functions of random variable. All right, so let's still remember that Bernoulli variable T. So let me copy that Bernoulli random variable from the previous page. I think is t, this random variable, there are two cases, -1 and 1. The probability of -1 is 0.1. The probability of 1 is 0.9. All right, so this is my Bernoulli variable. So then I actually can calculate its function's expectation. So in this case, I'm just treating this function as g. It's a gt function, which is 2t. Then how could I calculate e2t's expectation? Very simple. You only just replace the previous page v part into gv part, again, times that probability portion of x equal to vi, and then same. So I do 2t times 0.1 is the probability of p equal to -1, and then plus 2 times 1 times 0.9. This is the expectation of 2t. In fact, e scalar times a random variable equals the scalar get out and times et. So I hope you still remember, like we can write even this. E ax, in fact, equals to aex. All right. So there are actually many such corollaries, about the expectation. So next one is variance. So in fact, variance, you can think about just expectation of a function of this x minus mu quadratic function. I take expectation, and you use everything just from the previous page, if a random variable's function's expectation, and then you just replace that function to this exact form, and then you got the definition of variance. So this really variance captured the spreadness of your points versus the mean. So here mu is actually your mean, is the ex. Oh, I already have it on the right. Okay, so this is very basic, and I hope you still remember and very fluent in this, because we're going to use mean and variance a lot in many of the coming sections. Okay, so now you remembered what is mean, what expectation. So the whole idea is, okay, so I can't use training error as it's my goal. It shouldn't be my goal. So minimizing training error should not be my goal. Then what is my goal? So my goal is generalization, right? So how do I define generalization error? So one way to define that generalization error or future error can be defined by this, called expected prediction error. So let's see the equation. So equation really is, first is a expectation. I'm taking expectation of on top of a loss function. This loss function is defined as a L. And this L is defining the differences of the true y and my predicted fx. So in this case, for example, we can just use the square error loss, just like our regression case we used. All right, so we just replace that function into true y minus fx and take a square. So now the question is, what is the probability we consider? Because it's expectation, right? Expectation has to be about a random variable. So what is my random variable here? In fact, the random variable here is the xy combined random vector. All right, so we assume your input x is random variable vector. Your output is also random. You concatenate them together. This is a concatenated random variable. And then what's the probability is this joint probability of x and y together. And the expectation we are taking is on top of this joint probability. Consider both the x and y. So we can call that population distribution. All right, so what we are trying to truly minimize is we are trying to minimize the expectations, or let's see the function mean. This loss mean consider all the population xy pairs. Okay, is this clear? Please type in the chat. So if you think about it, this is not even just future, this is actually everything, right? I'm trying to minimize, I'm trying to minimize the expectation, consider all of the possible x1 pairs and follow this PR distribution. I see, the joint probability. Yeah, so the joint probability, I will actually cover it next time, the joint probability. So because it's very basic, so assuming I have a flip a coin, right? So that's what I did, T1, and I'm flipping the first coin. I'm also flipping the second coin. The first coin is a first random variable. The second coin is second random variable. The probability, consider P1, P2. So it's the first. So I want to look for the distribution of first is heads up, second is heads, it's tail up. So what is that probability? So I want to understand what's the probability of both are heads up. What's the probability of both are tail up? Okay, so, or the other switch. There are, in fact, 2 times 2, 4 different possibilities. And this is, if you can, give me, let me actually write head, tail, head, tail, and give me the probability of each of the cases, and you actually gave me the joint probability of these 2 random variables. I hope this explains this, but our case is actually much harder because our x is a lot more. There are many x. There's also y, and x not necessarily follow Bernoulli, y doesn't necessarily follow Bernoulli, but these joint, the semantic meaning is the same. All right. Okay, great. Yeah. So yeah, let me just example here. Okay. All right. So now the point is, I consider xy combinations, and then each one possible combination. What's the probability? The probability of that pair, xi, yi, or the cases. In fact, it depends on what type of probability distribution you use, right? It's a very complex probability distribution, but it's important. It's about pxy combination. And this equivalent to what? I'm considering all the pairs, all the possible cases, and I'm minimizing the mean of this loss by considering all the possible xy pairs. And this certainly is good if we can minimize it, right? Because it's not just, it's actually consider everything. And the point is, we can actually do a one-dimensional case. Think about it. So assuming it's the, let's assume it's a one-dimensional distribution. It's I don't want to use x because let me use z. So it's a z random variable. It follows a Gaussian. The fact is, I'm trying to minimize the mean is what? Think about if it's a Gaussian distribution. So I'm just trying to push the mean to be smaller. That's exactly minimizing EPE means. I don't have everything, but I can push the mean. Hopefully, by pushing the mean, I'm pushing the whole population, this loss, together smaller. So, but in fact, pushing the mean is a good measure. All right. So there are multiple concepts here. People also call this expected test error. And there's also a related concept called expected risk of a hypothesis class. And then the whole thing, what we are doing now, it actually follows. So if you convert this this integral, I mean, into something like this. Summation over I from 1 is my untraining data, and then L, yi, fxi. So I think maybe some of you already can recognize this. So what is this? This is in fact our training error, right? This is how we define on the training error. And this is called, this way, it's called expected risk minimization. Oh, sorry, it's called empirical. So because you are approximating the probability of xp or dx dy using your training data, and also there's no probability here, you're assuming a uniform probability on each samples. I know this is too much, but just related, what we are doing minimizing the training error, it can be, think about, it's an empirical approximation using our training data to approximate that integral term in this expected prediction error. All right. Okay, I hope this is clear. Okay, so this is too much, I know, but I still want some of you more like can understand this, because the choices we make by minimizing the training error, there's a reason that can behind that. And it's this empirical approximation of the joint population distribution. All right, so now even more questions now. Assuming we have this additive error model, so don't even worry if you don't understand it. So let's assume we have a true function called f here. We'll have a true function. This is my true function, f. So this is the true function. And because you estimate this from your current training data, right? That's just a sample of all the population X1 pair. So that's just your current estimation. So for the estimated from a specific D training data, we normally put a hat on top. So this is my estimated true F versus estimated F. So you can, back down a little bit. So this equation, you don't need to worry too much. It's just, you can decompose. So we already told you, right? This is the expected EPE error, right? So this is expectation. That's connect to the previous page. So how to calculate expectation? You have to consider x and y together, the joint probability. All right, so let's consider that. In this case, actually, it's a point-wide estimation. So, but yeah, still just you can use the previous pages to connect here. All right. So I'm trying to minimize this error and by minimizing this expectation. And I can actually, in fact, decompose this. I can decompose this observed y, because this is my observed y random variable, right? And y minus the true plus the trues minus the estimated. And this, in fact, so give me this part, it's called base error. It just, there's this intrinsic error, you can't use data to reduce it. And this just what your observation versus the truth, maybe there's some differences with the measurement machine. There's always a buffer. So assuming you try to, let's just use the simplest, maybe our pen size. This is my surface pen size. There must be differences with different pen size, but they are all seen in the spec as the one size. And that error, because it's the production error, production noise, right? It's not irreducible, okay? So that's that kind of error. So what we care then is this part. So it's the truth versus the estimated. So my true function versus my estimated, the function from that my current training data. And this part can be decomposed into something called variance plus Bayes quadratic term. So how to do it? So I will not do that. For my graduate class, I actually do this full proof. But so I have slides right after this slide. If you are very familiar with expectation and variance, you can totally do it by yourself. This is not difficult at all. Again, so think about EPE is our generalization error. It's my future or maybe whole population error I try to minimize. And this generalization error includes three things. The first thing is this base error or unavoidable irreducible error. And the second term is the error is something called a Bayes term, and the third is called a variance term. So that's just give you a rough decomposition. And the Bayes term is error due to incorrect assumption, and variance is error due to variance of the training samples. Okay, still too dry. Let's go on. This is my derivation, and you don't need to do it, but you actually can if you want it. The most important here is something, a concept. So I already told you, very important concept is the f truth, right? We have a true function. I'm trying to learn it. I have an estimated function from my current training data, from current D, so that's why it's conditioned on my training D, right? There's something else, it's expectation of f hat, which is very important. And this is called expectation of f bar. F bar is like this. You take expectation over all this training randomness. So again, remember what's the definition of expectation? It's a function or it's a random variable. So I told you in the beginning, fx is a random variable, right? Fx, that hat got from a D training data. All right, now I'm integral it out. Consider all of the possible distribution of my training data. That expectation is called expected estimated f bar. Okay, still too much, right? But remember this, very important is the blue line. I actually try to emphasize here. There's a f truth, f estimated from this data, and f bar is taking expectation of the f hat, the mean of f hat when you have many different kinds of training data. All right. Okay, so in the end, I want to show you actually, so it's this. So this is my EPE error. This is the EPE. And the first term is base error. And the second term is this fx minus the expectation. What I showed is f bar, just make it shorter. My current, there should be f hat here. Oh, actually, no, there shouldn't be f hat. So, okay, it's the f truth minus the f bar, and take a square. And this term is called Bayes. It's a Bayes quadratic term. It's as part of my generalization error. So think about the semantics. F is my truth, right? And f bar is its expectation. So when you have so many different kinds of training data, training sets, and that's the average f you're going to get. And this f true f minus f expectation means what? Means really on average, how different is my model, my assumed model versus the true model. So that's why it's called Bayes. All right, so let's now come back to the second term. The second term is this f hat versus minus the f bar, take a quadratic, and then take expectation. And in fact, f bar is what? F bar is the mean of EF hat. And this is exactly the definition of variance, right? Remember, what is the definition of variance? Variance is E of that function minus the mean of that function and take a square. And this is exactly the variance of my prediction F hat. All right, so hopefully this is clear. So this actually have a lot of other, to give you a further decomposition. You can totally do this by yourself, and how you can achieve this decomposition by just desegmenting the EPE error or ET, expected test error or expected prediction error or the risk. All right, so what you get is the generalizing error is a summation of Bayes quadratic plus variance plus the irreducible error. And this term, I have no way to control it, right? And then it's then the Bayes and variance. So this still sounds very dry. But let me back off a little bit. So what is even f in the predicted function, right? That f is the prediction. And this same formulation, this kind of decomposition, can be also used on parameter estimation. So I told you parameter can be considered as a random variable too. So we can think about there's a true parameter, assuming like I'm doing linear regression or polynomial regression. There's a true parameter theta. And from this data one, so from data one, I got the theta one estimated. From this training data two, because you really sampled the whole population, right? There's a lot of randomness in your training data. So just like I show you this cooking images, it's just on my iPhone, right? But you must have a lot of dish images in your iPhone. But those are also cooking images, right? I mean, just think about this randomness. I mean, the way I take pictures, the way you take pictures, the way the lights, maybe your phone, my phone, there's all these differences, but they are all cooking images, right? Okay, so from that D1, you got a cooking image classifier, theta 1. From you got a cooking image theta 2. And just so on and so forth, we got so many different kinds. I mean, depends on the randomness of your training data. Maybe on DT, so like you got theta T estimation. So you can actually do the same kind of decomposition. So assuming there's a truth, there's a true cooking image theta, that's the truth. So what's the error of my specific data generated theta versus the truth? And you can decompose it into, again, error due to variance of training data. So this part, the first part, is E theta hat minus theta bar, take a square. And then the bias term is this E theta bar. The theta bar is the mean. So let me do a bad version of taking the expectation. I'm just doing theta T hat, T from 1 to T. Assuming this is the one way I can get a theta bar. And the bias term is the theta bar versus the truth. So I can, from your figure, from your phone, got a cooking theta. From my phone, got a cooking theta. From all people's phone, we got different theta. We put them together, got a mean theta. Is this the truth? How this one differ from the true theta? And that's the bias. And how each di differ from this mean theta bar, that's the variance. All right, so you can estimate the errors of your parameter estimation also using this bias and variance trade-off decomposition. Okay, so enough equations. Now let's start to look a little bit visual geometric understanding. Again, theta is the truth. Theta hat is the one you just estimate from a sampled training set, and theta bar is the expectation considering the randomness of the training data. Bayes measures the accuracy. Bayes measures the quality of your estimator. How close on average is your estimator to the truth? And low bias implies on average we will accurately estimate true parameter from the data. Variance measures how precise is your estimator. So low variance implies the estimator does not change much as the training set varies. All right, so let's see what does it even mean. So this is the best figure I normally think like to understand bias variance trade-off. So here, the red dot, so the theta truth is the middle red dot. And for different training data, you get a different theta hat I, a different blue dot. Actually, blue dots, you have a lot of I is a set, right? Because the randomness of your training data. And theta bar is the mean point of your blue clouds. Of all blue. Okay, questions here because this is extremely important. All right, so let's see low bias first. Yeah, so I can maybe make it more concrete. So this is my first theta 1 from the first D1 data sets. This is my theta 2 from my second D2 data sets. And then so on and so forth. And there are many theta, maybe T hat. All right, so let's look at this really good one. Let's look at column wise because it's like 2 times 2, right? There's 4 things to consider. All right, so let's first see what do we mean variance. Let's look at this column, the first column. Variance is only about blue points. It's not about red points at all. Okay, keep that in mind. Variance, it's only about blue points. Only blue. So the reason why the first column is low variance is because the mean is very close to all the blue points. If you have question, type in the chat. I think it's very apparent. Low variance means that mean point is this blue cloud is now spreading over too wild. All right, let's see the high variance. It's only about, so the variance, it's only about blue points. Okay, so high variance. So let's look at the right second column. The second column, again, it's not related to the red points. And both blue clouds are very spreading over a lot, right? So that middle point, mean point, is so far, actually, it's pretty far consider this population. The population just spreading over too much. All right, so this means high variance. All right, so we're done with the variance only about blue. Yeah, it's only about blue, so I think this page I was trying to plan to talk about only the blue points, and we already talked about it. So yeah, maybe this is a cleaner page. Let's look at this. So now let's look at only the rows. So the bias, so and now the bias, so low bias, right? Okay, so bias is about red versus the center blue, the center of the blue. It's not about the spread over of blue at all. It's only about center of the blue versus the red. The reason why this is a low bias because the center is so close to the red, and this one, it's also the center is so close to red. It's just very apparent. And let's look at the high bias. The high bias, again, center so far away. And again, center of the blue versus the red, so far away. This means high bias. Okay. Question, type in the chat. So I think next page this is the point about the bias. Yeah, bias is the theta versus the theta truth. Theta truth is the red. Middle of the blue is the theta bar. It's the mean, right? It's average. Okay. And low variance just means my center blue is so close to all the blue. The high variance just means my blue is spreading over so much. Okay, so I think that's, yeah. All right, so what we normally observe, there are two cases. One case is this high bias case, and the other is high bias and low variance. So this is one case we always we figure out in our data, and the other case is this high variance and low bias. So let me ask you, because if you understand the semantics already, what is the high bias low variance model? What we previously naming about this? It's high bias and low variance. What do we mean? I mean, the issue of the fitting. It has really high bias and low variance. It's actually difficult for now because I haven't connected to, when you have a high bias model, which means I'm predicting so off, right? I'm predicting so off. This so off means actually high bias. High bias and low variance. In fact, my model is just so off the truth, but my model is so rigid. Whenever it's low variance, like rigid model, right? So rigid, it's not flexible enough. Oh, it's rigid. So this is in fact underfitting. All right, yes. And then in this high variance, low bias regime, okay, so here my model is so flexible. Yeah, I think this is actually a good one. Yeah, sure. High variance low model. So from my data, so I might be very off. So okay, so from this theta 1, theta d1, I'm actually pretty far from the truth. But if I have enough of training data and I actually measure, and I will actually get that truth. So, but just for my current this theta d1, it's actually very off. And this is in fact underfitting. The high variance, low bias is normally a reason of, sorry, it's not underfitting, it's overfitting. So again, remember this, what you actually observe on your training data is only one blue point. Yeah, so this is generalization error. So the training error maybe because so yeah, let's see the next page. So underfitting is normally model is too simple, too rigid to represent all the relevant characteristics. It's normally the reason because high bias and low variance. And what you observe is high training error and high test error. And overfitting is models too complex and fits irrelevant noise in the data. Maybe just you're so unlucky that specific D1 training data is just bad. I mean, there's so much randomness. So your theta is actually theta I, it's very off. But if you have enough, I mean, you take the mean, you actually can measure the truth. So this is normally caused by high variance problems. And what you observe is normally low training error and high testing error. Okay, so this is the end of the first module. I'm going to close